Welcome back. We are looking at Fan-Chen grain growth model. We are looking at the octave script for implementing this in a case where there are 6 different orientations. We have had an initial random orientation for each site given, and now we are into the evolution part of the code. So, there we had to define this partial derivative of the bulk free energy density with respect to eta, and that was called G. So, with respect to the I, there is G I. So, because there are 6 variants or 6 different orientations, we have 6 G's. So, G 1 for example is minus eta 1 plus eta 1 cube plus 2 eta 1 times eta 2 squared, eta 3 squared, eta 4 squared, eta 5 squared, eta 6 squared. So, it looks very complicated, but it is very simple. So, when I say G 2, then I have minus eta 2 plus eta 2 cube plus 2 eta 2 into eta 1 squared, eta 2 squared will not be there, 3 squared, 4 squared, 5 squared and 6 squared and so on. So, similarly we have G 3 which is minus eta 3 plus eta 3 cube plus 2 eta 3 into eta 1 squared, eta 2 squared, eta 4 squared, eta 5 squared, eta 6 squared, and minus eta 4 plus eta 4 cube plus 2 eta 4 times eta 1 squared, eta 2 squared, eta 3 squared, eta 5 squared, eta 6 squared and so on and so forth. So, for 5 also and for 6 also. So, just to make sure that we have written the expression correctly, it is eta 5 minus eta 5 plus eta 5 cube plus 2 eta 5 into 1 squared, 2 squared, 3 squared, 4 squared, 6 squared, and minus eta 6 plus eta 6 cube plus 2 eta 6 into 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So, now we have all the G's that we require. Of course, we need to take them to the Fourier space. So, G 1 hat, G 2 hat, etc. up to G 6 hat, it is a 2D Fourier transform. So, we take these G's and we take the etas to the Fourier space, eta 1, 2, 3, 4, 5, 6 as Fourier transforms, and we know the evolution equation. So, to implement it, we first have to implement the periodic boundary condition and calculate the k squared, and now eta 1 in Fourier space is nothing but eta 1 minus G delta t by 1 plus 2 kappa k squared, and L is 1 in both cases. So, I have not put it here, but we can put it. So, we can make it L 1 into dt by L 1 1 into kappa 1, and it is the same in all cases. So, we are going to assume that L 1, L 2 they are all the same, but let us put it. Okay. So, this will become L 3 into G hat divided by L 3 into kappa, this is L 4 into kappa 4, and this is L 4, and this is L 5 into G hat divided by L 5 into kappa 5, and finally, this is L 6. Okay. So, this L is the only thing that is missing. So, we have put. So, this is consistent with whatever expression we have assumed, and after that of course, we have to take them all back into real space, because the G's are to be calculated in real space. So, after every 2 time steps, again I am going to calculate this B and I am going to plot, and then the outer loop is for the other time unit. So, this will plot it so many times. So, this is the code. So, let us go to Octave and let us source this grain growth Fan-Chen .oct. Okay. So, of course, initially everything is 0, because at every point except for one grain the rest are 0, then it starts forming these grain structures. The blue actually represents regions where the value of B has become 0, which means that in these regions some grain is going to get 1, the rest are becoming 0. So, that is what the boundary structure that is developing. So, as far as I remember, all these yellow and red are regions where you have the non-zero values. So, you can see that there is one grain that is developing here, another one developing here, probably one or two are developing here also. Okay. So, this is what is evolving. So, it was a very short amount of time in which we have gotten this. So, we can run this code with a slightly longer time steps, so that we can clearly see what is the kind of microstructure that is developing. So, let us make it 5 instead of 2. So, every 2.5 time units once, suppose we start plotting, then what happens to the structure. Okay. So, it will take slightly longer than the previous code, but it will start developing the structure. Initially everything is 0. So, everything is almost like an interface, and then there are regions where it starts becoming 0, and you can see that it is already consistent with periodic boundary condition. This and this is the same, this and this is the same, and this and this is the same. So, it is doing that. The evolution implicitly, because of Fourier transform, assumes periodic boundary condition and starts developing this kind of structure. Okay. So, this and this remains the same grain, and this is one more grain, probably there is another grain that is coming up, and between them. Okay. So, this grain that came up, now it is growing, and because of periodic boundary condition, here also it is showing up. Okay. And so that now is evolving. So, you can see lots of grains, and between the blues, if you see a boundary, that means this is a different orientation, this is a different orientation. Okay. If not, it will just become one single blue patch. If it does not become, that means that it actually shares a grain boundary with the other region. Okay. So, that is what we are seeing. So, all this is one grain, but this and this are different grains. Both are blue because some order parameter is 1 here, rest are 0, some other order parameter is 1 here, rest are 0, and the region in between them is basically the boundary. So, we will actually look at which grain is 1 here and which grain is 1 here, etc. After this calculation completes, but you can see the grain structure. Okay. So, this is a grain, and because of periodic boundary condition, this is part of this grain, and these two are basically part of this grain, and there is a grain boundary here. So, this is a grain, this and this is a grain, and this is a different grain, and this is a different grain, and this grain is different from this, and this is basically part of this grain. So, one grain is becoming really big. So, this is here, here, here and here. Okay. And by periodic boundary condition, actually this is also part of the same grain. Okay. So, this is the grain structure that now I have got. Now, if you want to know what is the grain that is there in different parts, of course, you can say mesh eta 1 and view 2. Okay. So, if you now go look at, so now it is only eta 1 that is printed, and you can rotate and zoom and you can see the structure. So, the grain 1 is there. So, this is all part of periodic boundary condition. So, it is the same grain, and then there is another one oriented grain in the middle. Let us look at grain 2 where it is. So, grain 2 is these. Okay. By periodic boundary condition, this is the same, but it has in 2 other places also. Okay. So, we can see that if you go to the 3D. So, you can see. So, these are the places where it is 1, rest of the places the eta 2 is 0. So, that represents the regions where it is grain 2. So, you can put eta 3 and view 2. So, to look at where it is grain 3. So, these 2 grains are basically 3 grain, eta equal to 3 grains, and you can see this is already, I mean, consistent with periodic boundary condition. This is slightly here, and half of it is here and half of it is here. So, that you can see very neatly if you do go to the 3D, right. It is very beautifully seen here. All right. So, now we can look at where it is eta 4, and again It's very nice. So, this is one single grain for where the 4 is non-zero, rest of the places 4 is 0. So, you can see this again is consistent with periodic boundary condition. So, let us plot eta 5 and this is the grain with eta equal to 5 and let us plot the last one eta equal to 6. So, eta equal to 6 actually has 1, 2, 3 grains are there with eta equal to 6. Okay. So, now so those are this one, this is basically the same, this is basically same. So, those are the 3 places where this eta equal to 6 is there. So, basically this entire region now is split up into grains of orientation 1, 2, 3, 4, 5, 6 etcetera, which is what is seen when you plot this B and let me make it view 2. Okay. So, it is very easy to see. So, there are these grains and each one is different orientation. So, there are many different ways in which you can plot these. For example, you can give a different color. For example, you can split this 0 to 256 into 6 parts and you can start giving colors to 1 as some say shade of red and 2 as some shade of blue and 3 as some shade of green and so on and so forth. So, you will also get microstructure which looks similar to this so called the orientation maps that one gets from EBSD that you can get from plotting also. But in this case I am interested in showing where the grain boundary is. So, these are all the boundary regions and this is again a region which has not completely become into a single grain. So, either this or this is going to eat this up. So, that is what is going to happen after a while. Okay. So, these are regions which are like a triple junction. So, this is a different orientation, this is a different orientation, this is a different orientation. So, there is a region in between. So, this is a triple junction or maybe more than 3, there are about 4 of them meeting here and this is a triple junction because there are 3 of them meeting here and so on and so forth. So, this is a model which describes the grain growth. Now, this model is also nice in the sense that there are lots of things that are possible using this model. The first thing to notice is that we have assumed a very simple minded model. So, from the material science point of view, one can say that different grain boundaries will have different growth kinetics, different grain boundaries will have different interfacial energies or grain boundary energies and what type of interfacial energy they will have and what type of growth kinetics they will have will depend on not just that grain's orientation, but the orientation of the adjacent grain or adjacent grains. So, you can try to put that physics by trying to come up with a free energy which will incorporate all this information. Okay. So, from a material science point of view, this is a very simple minded model. There is things, there are things that one can do to improve it and there are several models which have been there in the literature to do it. This is nearly 20 years old model. The second thing is you see that whenever there is a grain, one order parameter is unity, rest of the order parameters are 0, right. So, in that case there is not any evolution that is going to happen in that particular region. So, there are things that are possible to do numerically. So, you can write a code which will do calculations only where more than one eta is there or eta is having a value between 0 and 1. Wherever the etas are 1 or 0, in those regions you do not have to evolve the evolution equation. This becomes very important because see we have just looked at 6 orientations. If you want to do proper statistics and if you want to evolve and if you want to do it in 3 dimensions, then you should be looking at large number of grains. If you have large number of grains, suppose you say 1000 grains, then you are solving 1000 equations and solving 1000 equations on all the domain points. Suppose you are in 3D, so like 512 cube and 1000 equations is too costly. But if suppose you say that this is bulk of the grain, there is nothing that is going to happen here, only the boundary is where I have to concentrate, and then correspondingly your computational effort can be brought down. So, there are models or implementations which concentrate on this aspect. Okay. So, and the third one is of course related to the coding aspect, because you want to write a code to which you want to say, okay, let us take a case where there are now 12 orientations or 15 orientations. Now, my code is written by assuming that there are 6 orientations and everything defined accordingly. So, if you want to write a generic code which will generate a script which is meant for this particular case. So, then there are programming languages like Python for example, or scripting languages like Arc or Sed for example. So, it is possible to write a script to which you can say, okay, generate a octave script which is meant for some 15 grains or 15 orientations, and then that code will actually generate the octave script which you can then run and do the calculation. So, this is also true of most of the phase field models. Phase field modeling, when you are working with them, when you are developing new phase field models, there are mathematical aspects, there are material science aspects, there are programming aspects, and there are numerical aspects, and whatever is your interest, there is something to that interest that is relevant to phase field modeling. So, this is one of the reasons why I like phase field modeling a lot, because there is lots of things that can be done depending on your interest and your inclinations, and grain growth problem is actually an ideal problem, and in my opinion this is a problem which is still not solved that satisfactorily in the literature, both from an experimental point of view and from a modeling point of view, because we have some nice results in the ideal scenario in 2 dimensions and things like that, but in actual 3D and in real solids there are lots of things that are happening which are yet to be captured in terms of grain growth models. So, this is in that way a nice model, and as you can see 6 equations on a 64 by 64 grid is not difficult. So, probably you can take the model and run it on a larger system and see or modify it to do maybe 10 or 12 orientations for example, and look at microstructure. So, you can really generate nice looking microstructures. The other thing to do is to actually put different colors to different grain orientation. So, that involves figuring out how to give a coloring scheme in Octave. It is possible to split the given color range into the number of grains, and each orientation then is colored in a particular fashion. If you do that, then without all this boundary you can just look at the microstructure and say, okay, all these blues are one grain, one orientation, all these are second orientation, and so on and so forth. It is also possible, and the ideal case should be that you take an experimental microstructure, read that information into the phase field model and evolve in the model and evolve the experimental microstructure and compare. This is something that is attempted, but not done satisfactorily as yet. So, it is a more open ended problem, which is a kind of problem which is ideal to look at towards the end of this course. So, we are coming towards the end of this course, and so it is a nice problem from that point of view to look at, because there is so much that needs to be done using these models. So, I will stop it at this point. So, we will look at a different problem which incorporates some elements of grain microstructure with 2 phase coexistence. That we will do in the next lecture. Thank you.